So if we can test whether two population means are equal or two population variances, you suppose we can test whether two population proportions are the same. And of course, the answer is yes, we can. All right, we'd seen previously that whenever we talked about population proportions, the proportions were just an average of ones and zeros. We needed large samples in order to use the central limit theorem result there. So that's what we look at here again. We are indexing things in a similar way when we have two populations and two samples. So indexing the proportions and their estimators with a 1 if they come from sample 1, or population 1, and they're indexed by a 2 if they come from population 2. One of the notations I see in your book is here is just y equals, and so that I think previously we'd seen some of the y's. So here y is equal, y1 is equal to the number in the sample that have the characteristic of interest. Y2 is the number of individuals or subjects in sample 2 that have the characteristic of interest. Okay, so our interest becomes estimating the difference between two proportions or testing hypotheses about them, P1 and P2. We know, just like before, our Y1 bar and a Y2 bar, the difference between those estimated the difference between two population means, and that's the same thing here. Our sample estimates, P1 hat and P2 hat, when we subtract those, they estimate the difference between the population proportions, P1 and P2. Whenever we have an estimator has variance, and we find that variance, the square root of that variance is given by standard error. And so we've got a little bit of notation here to clean up. All right. So the variance of the difference between proportions, remember variances are always additive, so that's not a typographical error there. We don't ever subtract variances. Okay. So the variance of the first plus the variance of the second. Well, what we did back in the single sample case, remember the variance associated with a proportion was the population proportion times the 1 minus the proportion over the respective sample size. So that's the same thing we have here, those two being added together. However, if we don't know P1 hat, we can't get the population variance exactly, or P2 hat. So we have to estimate P1 and P2 with their estimators P1 hat and P2 hat respectively. And so those replace the population proportions are replaced with their sample estimates here. As mine's printing here, I've got a box here. It should be with a hat over it. So variance hat. Now yours may have printed that way. Again, it's a Microsoft Word, Adobe Acrobat battle I'm waging there to try to get that to work. Okay. So all that means is our estimated variance. Okay. So our estimated variance, or we could write it as S squared, and then with the subscript P1 hat minus P2 hat. So remember, for those variances, we have sometimes an index to denote which group it's from, but if it's a function, it says it's the variance of that function. All right. I mentioned it just a little while ago, but of course, if our central limit theorem results hold, okay, so recall the central limit theorem. These are actually sample means, and so that they will follow a normal distribution when the sample sizes are large. So P1 hat is normally distributed, P2 hat is normally distributed. When that sample sizes are large, the difference between them is also normally distributed. It's estimating P1 hat minus P2 hat has a mean of P1 minus P2, and we just looked at the variance expression on the previous page. The approximation is good if the large sample size condition is met, and so right now I'm not recalling it if I wrote those are strictly greater than or equal to 5 in the one sample case. So if I wrote equal to previously, then all those would also be greater than or equal to. Okay, it must be the case that all of these must be satisfied, not just some of them. So remember, in the case for just a single index, But if we were just to look at this is saying if our proportion is very close to 1 or very close to 0, we need a lot of information to do that well. Okay? And so we'd have to do that well then for both of our samples. Our confidence interval, or CI, for the difference between proportion 1 minus proportion 2, we take our estimator, plus or minus the critical value, which is Z, since we have standard normals, the central limit theorem at work there. And then this is times the standard error of the estimator, the square root of that estimated variance expression we had a couple pages back. Same plain English interpretation of that, right? Estimator plus or minus critical value times the standard error of the estimator. Under the conditions that we have random samples that are independent and the samples are large. So again, either greater than 5 or greater than or equal to 5. However, I've been doing that to be consistent. So no surprise there, other than I listed the confidence interval before I talked about hypothesis testing, right? So I usually talk about hypothesis testing first. Got a little bit more to talk about, though, with hypothesis testing. In the hypothesis testing case, I'm only going to consider the difference here of 0. All right? We know that for means we could talk about non-zero differences, and we could here as well, but we're just going to look at the hypothesized difference of 0, meaning are the two proportions the same, right? Okay, so like before, we said we're going to let H naught be true everywhere we possibly can. So that happens in the T statistics with mu naught in those formulas. That happens in the Z score that we compute for a test of a single proportion. That we put the P naught value in the variance expression. So here, if H naught is true, our two estimators P1 hat and P2 hat are both estimating the same thing, right? So it would make sense then, if H naught is true, then to put the information from those two samples together into one better estimator. Okay, just like we did with the variances. If the variances are equal, let's put that information together, come up with a better estimate. So that's what we're doing here. Okay, we come up with a pooled estimate for a common proportion. So P hat with no subscript versus P1 hat and P2 hat. So this takes all of those that exhibit the characteristic out of sample 1 plus all those that exhibit the characteristic out of sample 2 and divide by the combined sample size. So this Y1 and Y2 are what were defined back on page 1 of today's lecture. Okay, the number of successes in sample 1 and the number of successes in sample 2. All right? So this says this is the total number of successes divided by the total sample size that we look at. All right? That P hat value would be a better estimate of the proportion if H naught is true. Okay? Tests involving the equality of the population proportions should utilize this better estimate then. So when we look at the hypothesis testing situation, whether we're looking at two-sided tests or one-sided tests, for the difference between P1 minus P2, notice over here what happens. This is our estimate up here, P1 hat minus P2 hat minus the hypothesized difference of 0. So I don't have minus 0 written, but it could have. In the denominator here, it's P hat times the quantity 1 minus P hat. So what's going on down here is the same thing that we wrote here. Okay, I replaced this P1 hat and the P2 hats here with that common estimate P hat, factor it out, and I get this expression under the square root. Okay, I'm putting that, so this is imposing the condition in H naught everywhere I possibly can. If I still end up with something extreme, then H naught must not be true. All right, so that's what's going on down here in the denominator. Okay, we don't have that in the confidence interval because in the confidence interval we're not making any assumptions like we are when we have hypothesis testing. Just like before, then two-sided test, two-sided rejection region, right-hand test, right-hand rejection region, left-hand test, left-hand rejection region. Okay, all of our large sample size conditions must be met, and here I've got greater than or equal to, so we should probably replace those strictly greater thans before with greater than or equal to. Okay. From a January news poll of 900 registered voters, 17% of voters favored a young senator who had just declared himself as a candidate for president. In February, a second poll of 900 registered voters yielded 24% favoring the candidate. Can you conclude that the candidate experienced an increase in voter support? Okay, so what's different here is that we have two different polls. It's two different groups of 900. All right. If we look at a group, one of the things that we see about in the news today is is that we have a sample of size 900, and a percent of that 900 favors one candidate, a percent of the same 900 favors the others. Those aren't independent of each other, are they? They're coming from the same group. Okay. So here, a second poll is conducted, and so we're looking at different individuals. All right. So if this is the case, let's see. We have P hat for January. P hat for January is 0.17. Agreed. P hat for February is 0.24. In both cases, the sample sizes for January and February are the same. They wouldn't have to be in polling agencies. A lot of those I see online, though, you usually are at 900 or above. The one that was on your test that we just discussed was 910. So it depends on some of those. They see Fox News is usually around 900. So ABC has, it's either 1001 or 1101, something a little different with ABC News. All right, so here we have January. Our information for NP hat is what? All right, so NP hat we have 900 times our value for P hat of 0.17. We got to check whether that exceeds 5. And so here I have that's equal to 153, which is greater than 5. So that's okay. We have NQ hat for January would be 900 times 0.83. And that would be 747, which is greater than 5, and that's okay. For February, NP hat, again a 900 and times 0.24. That one makes, this one should, so that's equal to 216. And NQ hat, multiplying 900 by 0.76, I have 684. And both those are okay. So our large sample size condition is met. All right. Can you conclude that the candidate experienced an increase in voter support? So we need to pick an alpha because one's not given to us, is it? So what do you decide? Just pick. Or a 0.05 crowd, most typically. All right. So can I conclude that the candidate experienced an increase in voter support? So really, what's our research question? H1. Is that our January proportion? If it increased, January is smaller than February. Agreed? Then the opposite condition in the null. No difference. Okay? So we need this value of p hat. So remember where p hat was equal to y1 plus y2 over n1 plus n2. I need p hat for our problem here, don't I? All right. So where is y1 on this page? This 153 would be our y1, wouldn't it? Where would y2 be? Right, 216. Does everybody see where that comes from? This is an example where we're given the percentage, not the number that have the characteristics. So many of those we did in the single population cases that I gave you the number that had the characteristic, and this one doesn't do that. So when you multiply the proportion times the sample size, you're not only doing a sample size check, but how many have that characteristic, or how many successes were there. Okay, and then this would be divided by 900? No, should be divided by 900 plus 900, right? Now here the sample sizes happen to be equal, but if they weren't, we'd want to combine those. Look at in our combined sample sizes, how many total successes did we have? So y1 plus y2 is total success, n1 plus n2 is our combined sample size. All right, so when I do this, what do I come up with? Well, it better be something between these two. And if the sample sizes are equal, it will be right exactly in between the middle point. So what do you have? 0.205. Everyone agrees? All right, so whether this is a right-hand test or a left-hand test is up to us. All right, because we see it's one-sided. Are we going to take January minus February or February minus January? Does it matter? It doesn't matter. We want to make sure our rejection region corresponds to the direction of the test. And likewise, when we compute the observed significance level or p-value, we've got to go in the correct direction. Okay, so which one do you want? Okay, I'll pick. Let's go January minus February. All right, so our test statistic the formula is off screen, but we should have our z-score. If we're going January minus February, then our proportions need to go in that same direction. All right, January is 0.17. February is 0.24. We could write the minus 0. There it is. I didn't put it on there though, but the hypothesized difference is 0, so minus 0 doesn't change things. Divided by the square root of the quantity, still imposing the condition of the null hypothesis, puts this 0.2050 in the denominator times the quantity 1 minus 0.2050, that would be 0.7950. times the quantity 1 over 900 plus 1 over 900. When you add this together, clearly it's 2 over 900, but the reason that I write them both out, that way if we have different sample sizes, you know to put both of those, each sample size in there. All right, and calculate z. Better be a negative number, since our numerator's negative. What value do you have for z? That seems large. I'm going to break the tie.
Negative 3.5.
Negative. Four different answers. Anyone else? You may want to work them out in pieces, work the denominator maybe, and then numerator's the easy one, negative 0.07. And negative 3.6783 on my second attempt as well. I think my first attempt was something different. Must be something about that problem. All right, what's our rejection region? We're going to reject the null hypothesis if what? Left-hand test, left-hand rejection region. You're going to reject if your calculated value for z is less than or equal to negative z determined by tail area alpha, which is 0.05. So you're going to reject H naught if the null hypothesis is less than or equal to negative 1.645. All right. What's our conclusion? Is there a significant increase in candidate support? Yes or no? Yes? So there is a significant increase in candidate support. Our language is one-sided, reflecting that we did a one-sided test. We've used the word increase, but it was a left-sided test just because of the way we set it up. Our alpha was what? 0.05. We calculated a z-score of what we calculate, not what we compared it to. What we eventually calculated was 3.6783. Rounding to 2 decimal places, negative 3.68. What is your p-value? So you're using table A1, standard normal table. You calculate a z-score, stay on the z-table to compute the p-value, and you have what? P equals 0.0001. You want the left area associated with that. The right-hand area is given in the table as 0.9999. When I look at the news story, whichever one did this, the results are posted with a statement that says that the margin of error is plus or minus 3 percentage points. How does this margin of error compare to what you would compute for the difference between proportions in a 95% confidence interval? So we want to divide this page up into 2 parts. We're going to keep about 2/3 of this work area to answer this question, and then I want to make another point on the other side. So I'm going to do this so I mind my space. So if I wanted to look at a 95% confidence interval, now I realize we'd want a confidence upper bound for our left side test, but I'm just going to do a confidence interval because I want to tie this to the news story. So a 95% confidence interval for the proportion January minus the proportion in February. So our point estimate would be the 0.17 minus 0.24. 95% confidence intervals, so that means I'm going to have 1.96 for my z-score. Agreed? Our standard error, not going to use the pooled one. We're not assuming that there's no change. So that means I'm going to have 0.17 times 0.83 over 900 plus 0.24 times 0.76 over 900. So I have the negative 0.07 plus or minus 1.96 times this quantity in the square root. When I computed this, I got 0.0189. Do you agree? We may differ in a couple of 10,000ths due to rounding error. So I have negative 0.07 plus or minus 0.03 0.072. And so that the difference here is negative 0.1072 up to negative 0.0328. This interval is entirely negative, so that is a confidence interval. I feel 98% confidence that there is a difference, and then can further conclude that February is larger because the interval is entirely negative. It's not exactly the same as the one-sided test we did. All right, here we have this 0.03 given here. That this is not the margin of error they're talking about in the news story, though. In the news story, they compute confidence intervals on a one-at-a-time basis, most usually. Okay, so this generally is not what they're talking about, because this would round to 4%. They usually only give it as 0.0 something. All right, so what is it that they're computing? Okay, on the other side here, consider what you see is that they're giving you a January report, and in January they say it's 17%, and at the margin of error they write plus or minus 3%. February they write 24% with a plus or minus 3% margin of error. It's typically what you see reported in the newspapers and in news publications. All right, so that's that plus or minus 3% margin of error. All right, that's that capital E that we calculated in the sample size. Determination formulas. So if we write that as our Z is 0.025, there is a confidence statement on several of those news stories. I'll see if I can find one for you. Then it doesn't. Which one do we want to do here? 17% or 24%? Let's look at 24%. And for this, I'm going to need your calculator because I did it for 17%. I want to compare what they are. All right, so this 1.96 is going to replace this Z with 0.025 times this square root quantity. And tell me what you have. Point 0.0142. Point 0.0279. Anybody else? You may not have multiplied by 1.96. 0.027 something, fourth decimal place. Point 0.0278 and 0.0279 were the two I heard. So this one is actually for the 0.24. If we did, when I did the p hat equals 0.17, the margin of error I got is 0.0245. Now, if you have a calculator handy, this one will be even easier. What is 0.5 times 0.5 over 900? Use 0.5 instead. Remember when we did sample size selection, when those proportions were closer to 0.5, the margin of error was bigger. So it probably should have gone up. And so here this is 0.17, it's smaller. When it went up to 0.24, I got 0.027. What do you have at P equals 0.5? Anybody? 0.032, 0.033 if you round. Okay, so that's the biggest it's going to be. So when they report this plus or minus 3%, clearly it's not the same for both of these guys, these two proportions. So it looks like what they're doing is probably more along the nearing 0.5. They don't say that when I read their reports. Okay, because if they actually did that for 17%, it rounds down. It wouldn't round to 3%. Okay, but they always report the same plus or minus margin here, and they're always in those that 1 percentage point. They're going to be at the same percentage point, especially when those proportions are close to 0.5 in some of the close races, such as we're seeing this year in our presidential race. But just in general, you look at those. So typically, whenever you see the news reports written like this, they're not giving you this margin of error. They're giving you the margin of error for an individual proportion, not for a difference between proportions. Those are largely dominated by sample size. So that if you want a 3%, you pretty much need to be over 900. Okay, if you want a 2% margin of error, then you can use 0.5 and figure out at least what sample size do you have to get to 2%. But sample size is what dominates that. So that's typically why you see values for sample sizes on these surveys, 900 or 1,000, is so they can get to that 3% margin of error. Some years back, before everything was automated, telephone calls, that they do all these before all that, you see a lot of plus or minus 4% and sample sizes in the 500 and 600 area instead. Okay, so anyway, just a little bit of stuff about what you see on television or in any of the news stories you may read online or hard copy. I think it's interesting. So it's interesting that they're becoming more. They're releasing more of their information than they used to, and probably because they're also doing a better job. So. Hypothesis testing. Required large samples. Well, what if? Remember, this whole course I said is about what ifs. What if it's not? All right, what if the samples are not large enough? That's one we can't fix in this course. We can fix it, but not in this course. So there is a non-parametric alternative. So what we're doing are called parametric tests. Parametric tests means that we have an assumed distribution with assumed parameters, normal 0, 1 for this one anyway. All right, so there's a non-parametric alternative. So non-parametric means there's not an underlying distribution that we're assuming. And so that if you wanted to learn more about non-parametrics, then there is a non-parametric methods course that can be taken. What if the samples are not independent? This again is a non-parametric test. That the McNamar's test is taught in non-parametric methods. Okay, so just let you know, so that whenever we look at this information here, what if I can't get large samples? I tried, but I didn't, based on my proportions, I didn't. And so often whenever I work with folks on doing their surveys, the group they're surveying, perhaps the population they're surveying, the population is only 200. And so getting a sample size that's large enough is going to be tough. Or So without surveying the entire population. So what if large samples aren't feasible for some reason? Either something happened with your survey tool, in this with proportions, we're typically looking at a survey instrument. Something happened, there was a problem with the survey itself, we didn't get the answers, something happened in the mail, the email failed, or whatever the case may be. So for some reason I did not get the large samples I anticipated. Does that mean I'm just totally sunk? No, we may have some non-parametric alternatives. Now, if you remember, we talked about statistical power. Okay, the ability to detect differences that are truly there. Well, if you lose sample sizes, your sample size gets smaller, you're sacrificing power, right? Intuitively that makes sense. If I'm not looking at such a large fraction of the population, then I can't be as confident about what I'm finding, right? I'm going to be able to detect differences better if I look at more. And that's intuition. That makes sense. So whenever you start looking at small sample sizes, and that may be a reasonable restriction, but you probably are going to sacrifice power. That's something to be aware of. So you're not going to be able to detect differences of 3 and 4% probably. You're not going to be able to detect that. You're more likely to be able to detect differences of 10%. Is that narrow enough? Okay, so it becomes a power question. And so even though we don't spend time doing power calculations here in this course, we're aware of what power is. And so we want to, if we're going to do a study, we want to make sure, do I have good statistical power to do this? All right, it may be convenient to have small sample sizes for a particular application, but what am I sacrificing with regard to power? That's a big question and an important one to be able to answer.